Hey everybody, and welcome back to Patel Academy. Today I wanted to go over the 2018 free response questions for AP Chemistry, and I wanted to show you guys some of the major concepts and some of the types of questions that might come up on the upcoming AP exams, as well as point out some key errors that students may have faced when they were writing the exam so that you guys don't face the same problems and you guys are able to ace your exams and get a 5. Now, this will model a timed walkthrough, so I'll try and obey the time limits that are given by College Board, which is the first 3 long answer questions at about 20 minutes to 23 minutes each, and then the last 4 free response questions, short answer ones, for about 9 minutes each. Now, if I do go a little bit above, it's because I'll be going on slight tangents to explain some of the concepts to you guys. So just keep in mind that when you do your exam, because you're not going to be explaining all this stuff, you guys will definitely be able to stay within the time limit. Alright, so let's get right into it with question number 1. So question number 1 says a student performs an experiment to determine a delta H reaction for a redox reaction above. 1A says determine the oxidation number of Cl in NaOCl. Okay. So I'll write out NaOCl, which is the molecule we're focusing on. Keep in mind, now we see that this is a molecule with a neutral charge. There's no charge on it, and that means that the sum of the oxidation numbers has to become 0. Now, one of the other things that we know is that we can actually break apart this molecule into 2 separate ions. So I'll write that in orange underneath. So we have Na plus, and then we have OCl minus. Right, so these are the 2 ions that we have. Now keep in mind, for this Na plus, the rule for assigning oxidation numbers is that because it's an element with a charge, so it's an ion, the oxidation number has to be the charge. So Na has to be +1. Now OCl is a polyatomic ion, and so the sum of the oxidation numbers on the individual elements has to add up to the charge. And so the oxidation number of oxygen and then the oxidation number of chlorine has to add up to -1. Now, what we also know is that oxygen almost always has a -2 charge. There's only a few cases where it doesn't, in the case of the O2 2- molecule, or in the case of peroxides. And so what we can see here is, because this doesn't follow any of those exceptions, our oxygen is going to be a -2, and thus chlorine, which is what we're looking for, has to be +1. So if you remembered your oxidation naming rules, you'd instantly be able to get that question. Now 1b says calculate the number of grams of Na2S2O3 needed to prepare 100 milliliter of a 0.5 molar solution of the compound. Okay, so this one is also just some basic dimensional analysis, or stoichiometry. Not stoichiometry, sorry. Just some basic dimensional analysis and some basic formulas. So you need to be able to tie in concentration to mass. And so the formulas that we know are C is equal to N over V, which means that N is equal to C times V. And then we also know that the number of moles is equal to mass over molar mass. And so moles times mass, molar mass is equal to mass. And this is what we're looking for. So it's just a matter of working through the different steps. Now, you could do this dimensional analysis way, or you can do it in terms of the individual formulas. I believe both ways are accepted. As you move on, though, dimensional analysis might be a little bit more helpful, so I'll try and outline that method over here rather than doing just the formulas. But I believe in my previous AP Chemistry walkthrough, I did use the formulas. I'm just trying to show both ways. Personally, I think that if you do each formula individually, it's much easier to keep track of your errors if there are one. But if you feel confident in your calculation, then dimensional analysis ensures that your units are going to be accurate at the end, so you don't have to worry about that. So for this case, in dimensional analysis, you traditionally put this unknown quantity first, this known quantity at the very start, so 100 ml. I'm going to multiply that by, well, first I want to convert it to liters, and so I get, or I guess I can do it, yeah, I can do it like this. So there is 1 liter per 1,000 milliliters, and then times our concentration, so I have 0.500 moles per 1 liter. And so what you'll notice is that stuff will cancel out, and so we will get 0.05 moles. So that's the first step. And the second step, I'll do it on the next slide. So we had 0.05 moles And then what I also know is that by looking at the molar mass of Na2S2O3, which you can calculate by using the periodic table that we're provided, you just add the atomic masses in the appropriate ratios, you should get 158.1. And so I see I get 158.1 grams per 1 mole. Now this is grams of Na2S2O3. I'm not going to write that out, but actually I can. Won't take up too much space. So grams Na2S2O3. And so what I'll be left with when I multiply these together, 58.1 is 7.905 grams, and then with significant digits in play, this would round to 7.9. So this would be 7.9 grams of Na2S2O3. And that is part B. Now for part C, it says using the balanced equation for the redox reaction and the information in the table above, determine which reactant is the limiting reactant. Justify your answer. Alright, so keep in mind that the limiting reactant or the limiting reagent is based off of the stoichiometric ratios and based on which reactant would get used up the fastest or first if we had some set of quantities among all. And so with this table, we see that the concentration and the volume are identical. So if you consider the formula that I just mentioned, the number of moles is concentration times volume. Well, each of the mole values would be identical for each of these reactants. And so then we have to consider the stoichiometric coefficients. And so we see that for every mole of Na2S2O3 that gets used up, we use up 4 moles of NaOCl and 2 moles of NaOH. And so you can probably tell that because we're using 4 of something opposed to 2 or just 1 of something, the 4 would get used up first. And so based on that logic, we can say that the NaOCl would get used up the fastest. So our limiting reagent would be NaOCl, and this is by our stoichiometric ratios. Now definitely when you're writing your actual exam, make sure that you write out your paragraph responses. So, or maybe not full paragraphs, but at least sentence responses. So don't just write NaOCl, be sure that you justify based on what I just said regarding the stoichiometry. Okay, part D says, according to this graph, what is the temperature change of the reaction mixture? We're given that the solutions are originally at 20 degrees Celsius, so I'll just write that Ti is equal to 20.0 degrees Celsius, and that the temperature of the reaction is shown in the graph up below. In this graph, we see that it levels off at about 32.5. degrees Celsius. And so our delta T is going to be 12.5 degrees Celsius. Now this will come into play because if you remember originally, we're talking about enthalpy, and I believe the next question is going to involve enthalpy. We're releasing energy because our temperature is increasing, so this is an exothermic reaction. So keep that in mind when you're thinking about sign conventions or when you're thinking about just any conceptual questions. This is an exothermic reaction. All right, so part E. Question 1 says, calculate the magnitude of the heat energy in joules that is released during the reaction, and assume that the specific heat of the reaction mixture is 3.94 joules per gram Celsius, and that the heat absorbed by the calorimeter is negligible. So before I start, I just want to point out that both of these things that we're told to assume are common assumptions made when you're doing calorimetry experiments. You want to make sure that you're not taking into account or that you have a negligible amount of heat absorption by the calorimeter or the environment, that the specific heat is very closely modeled by the specific heat of water. And so when we're calculating the magnitude of heat energy in joules, keep in mind that this is our Q value. We use the formula QE is equal to MC delta T. We're given our mass is 15.21. Our C value is 3.94. and our temperature is 12.5. And so when we multiply these together, 15.21 times 3.94 times 12.5, we get 749.0925. And oops, this will round to 749 joules, as the question asked. The units are joules. Okay, now we have to consider using the balanced equation for the redox reaction and our answer to part C, calculate the value of the enthalpy change delta H reaction in kilojoules per moles of reaction. Okay, and it says include the appropriate algebraic sign with your answer. So this is where the thing that I just talked about comes into play. We know that this is exothermic because there's a positive change in temperature, so it increases. So we should immediately know that our delta H is going to be negative. It's going to be less than 0. Okay, so we have to do this in terms of the moles of a reaction. And so first, it says, using your answer in part C. That should immediately clue you in on the fact that you're supposed to calculate the number of moles of the limiting reagent first. So that's going to be N of NaOCl. If we scroll up to their table, remember that moles is concentration times volume, so it's just going to be 0.5 times 0.005 because we're converting our milliliters to liters, so this should be 0.0025 moles. Now we want to calculate the moles of reaction. And so to do this, we have to utilize a stoichiometric ratio. And so we see that we consume 4 moles of NaOCl every time 1 mole of the reaction goes through. And so for that, we essentially need to do 0.0025 moles times 1 mole of reaction. This is the dimensional analysis method again, divided by 4 moles, technically NaOCl. I didn't write that over here beside the 0.0025, but it's implied. You should write it out. I didn't have the space to do it. And so you get 0.000625 moles of reaction. These kind of small calculations, I would advise that you guys should try and do these in your head because it'll definitely make it much faster than if you were to plug in even these small calculations into your calculator. And that small amount of time could stack up and mean that in the end you have an extra 5 minutes to ensure that you check all your answers and get the correct one for each. So just keep in mind. So now that we have this, we have to consider is our delta H total is equal to our negative Q value because it's exothermic. And so our Q value that we got before was 749 joules. So this would be negative 749 joules, which is equal to negative 0.749 kilojoules, right? Okay, and so now we have our delta H reaction. Now, in case you don't know, that degree sign beside the delta H just represents that it's done in its standard state. So everything is in its standard state temperature. And so we say that that is equal to our delta H total divided by our moles of reaction. So now we have all the values that we need in order to solve this question. And so we go negative 0.749 divided by 0.000625, and we get negative 1198.4. kilojoules per mole, which would round to, if you wanted to do this in scientific notation, it would be 1.2 times 10 to the power of 3, or you can just write 1200. Kilojoules per mole, rounded because of significant digits. Okay, so that was E part 2. Now we're going to move on to part F. Part F says the magnitude of the enthalpy change in kilojoules per moles of reaction calculated from E part I, from the second experiment is the same as the result calculated in part E2. What we see is that the student repeats the experiment the second time by doubling the volume of the reactants. Okay, so explain why the magnitude of the change is the same both times. Okay, so in these types of cases, this is me personally, but I prefer a mathematical explanation more than a conceptual explanation, just because I feel like if you do it mathematically, it's much easier to get your point across. And so what I'm going to say is that in the end, so for the second experiment, our delta H reaction is going to be equal to we still have our MC delta T, right? But now it's going to be 2 MC delta T. So because we double the volume, we're going to double the amount of moles. Because we're doubling the amount of moles, we're going to double the temperature change. And so what we're going to end up getting is 2 MC delta T. But then when we divide by the number of moles, we're going to get 2N, right? We double the amount of moles, but we're also doubling the energy change. And then because of that, we're still just left with delta L, right? This is delta H prime, and this is just our normal delta H reaction because it all cancels out. And so because of that, we see that the magnitude is the same. And this is why this is one of these common errors that students may make, where they expect, not like here it explicitly said that show or explain why the magnitude is the same, but sometimes the question would say, we doubled the volume of the reactants but left the concentration the same, calculate the magnitude of the enthalpy change. And so people will often get a different result because they'll forget to account for the fact that there's a change not only in the number of moles, but consequently a change in the total amount of energy produced as well. And so because of that, the magnitude remains the same. It would be a different story now if something else may have changed. So if not just the number of moles, but because of that, if there was some sort of a function or something that made like the mass go up as well as the temperature go up, something like that, then there could be a slight skew. But in this case, with just the number of moles, the magnitude will remain the same. So that was just a little tangent over there. Part G. Now part G is a fairly simple question, short and sweet. It says write the balanced net ionic equation for the given reaction. Okay. So I'll scroll back up to the reaction, and so what we see is that we want to find our net ionic reaction, it said. Sorry, I forgot the question. Yeah, the balanced net ionic equation. Okay. Well, what do we know is common across all of the different, I guess, compounds you can call them. There's an Na, and the Na does not change its configuration or its bonding necessarily from out of a polyatomic ion and into its stable state ion. So we're constantly left with an Na continuously, so we can actually eliminate those. The reason why I said that is because if you take sulfur, for example, it first appears in S2O3 on the reactant side, but then it changes into SO4 on the product side. And so that is a change that you have to record in the net ionic reaction. So what students sometimes get confused with questions like this is that there's no precipitate, so they don't know what to actually include in the net ionic reaction. And so when there's no precipitate, you have to consider, well, are there any compounds that are being completely broken apart in terms like polyatomic ions that are being broken apart and then restructured into a different compound? So S2O3 into SO4. Now, one of the other things to keep in mind is that H2O, we can rewrite that as H and OH. And so because the OH stays the same, we don't need to include that necessarily as a separate ion. We will, however, consider the OH in the net ionic reaction because it breaks apart from NaOH, but I'm just saying, and it forms H2O as its own compound, but it's technically not a break apart. So our net ionic reaction in this case would be S2O3. Now the charge here would be 2 minus plus OCl minus plus 2OH minus. So once again, the reason why I'm including OH is because technically it forms a new compound H2O where the bonding is slightly different compared to NaOH. However, I'm just saying that for other questions, the OH ion is still the same in NaOH and water. And so this ends up forming, I'll write it underneath. Now we have 2, so 4, 2 minus, plus, so this should be 4 OCl, plus 4 Cl minus, plus H2O. And so I believe that is the net ionic reaction. Now, of course, include the states. I realized afterwards that I forgot to. So all of these should be AQ except for H2O, where I specifically wrote liquid because I had the space. But all of these you have to include indicate that they're aqueous to get the full marks. So yeah, we got the charges, we got the coefficients, so everything looks balanced. So yeah, just keep in mind that don't be fooled with the OH thing. While in principle it stays the same ion, we have to include it in this case. Okay. Question 2. A student investigates the reactions of nitrogen oxides. One of the reactions involves an equimolar mixture of NO, so nitrous oxide or nitrogen monoxide, and NO2, so nitrogen dioxide. The particle level representation in the flask at the completion is shown on the right. In the box on the left, draw the representation of the reactants. Okay, drawing is always fun on the AP exam. Usually a draw question means a much simpler question than some of the other calculation heavy ones. So I'll use white for oxygen and I'll use black for nitrogen, just to indicate a similar color scheme to theirs. So it says draw the particle level representation of the reactant that would yield the product mixture on the right. Okay. So first on the right, let's see what compounds we see. So I see NO2, I see 4 of them, and then I see NO, and I also see 4 of them. And so what you have to consider here is, okay, there's some NOs that get carried over. So we would be left with, so we know that we have to have at least 4 NOs originally. So I'll draw those in first. So those are 4 NOs that got carried over. Now, the reason why I know that there's 4 NOs and how I'm going to come across the other ones is because of the stoichiometry of the reaction. So they're equimolar, but we can consider the ratios that appear between the different compounds. And so what we see is that the 4 NOs have to be carried over, and then we're going to be left with a total of 4 NO2s. Now, 4 NO2s means we have 4 nitrogens and 8 oxygens. And so the way that we're going to be able to distribute these is through another 4 of these NOs, nitrogen monoxides. So now as you can see, we're left with, we have, is that 7? That's 8. So we have 8 total nitrogens on the reactant mixture, and we have 3, 4, 5, 6, 7, 8 nitrogens on the product mixture, so that's correct. Now we just have to account for our oxygens. So on the right side we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And on this side we only have 8, so that means that we need 2 O2 molecules. And that marks the entire reactant mixture. So you just have to use the law of conservation of atoms. In this case, there is a little bit of stoichiometry. However, in this case, the ratios don't particularly match up because we're told that it's equimolar. And so because of the limiting reagent, we don't necessarily know the quantity that was put in. And so because of that, you can't exactly use stoichiometry, but you just have to use the law of conservation of atoms. And so in this case, I think the points were allotted for the count as well as for atom conservation. So it's a very free 2 points. All right, 2B. So 2B. Okay, so the student begins with an equimolar mixture of NO and NO2 in a rigid reaction vessel. Now we're in a different reaction where we're forming N2O3. Okay. And the mixture reaches equilibrium at 298 Kelvin. Calculate the value of the equilibrium constant K for the reaction at 298 Kelvin. Okay. We're given information on delta H, delta S, and delta G. So we're given information on enthalpy, entropy, and Gibbs free energy. So we can't use our traditional method of calculating K, which is through a Rice table or an ICE table, but depending on how you want to call it. But we can use one of our applications of thermodynamics formulas. And so what you might know is that there's actually a relation between spontaneity, so Gibbs free energy, and equilibrium. And that relation is given by delta G is equal to negative RT ln K. So I'll write that down. So delta G is equal to negative RT natural log of K. So solving for K, well, K is equal to e to the power of negative delta G over RT. So this is just simple algebraic manipulation. The inverse of the natural logarithm is the exponential with base e, and so we can solve for K this way, and then we just have to plug in all the information that we know. And so K would be equal to e to the power of, put it in brackets, we're given 0.87 divided by our reaction occurs at 298 Kelvin, and then our R value for this case we would use 8.314 joules per mole Kelvin. Okay, so we have this expression now. Oh, sorry, I forgot to make this conversion. This 0.87 has to be converted into joules per mole because our gas constant 8.314 is in joules per mole Kelvin. And so this would have to become 870. So sometimes this is where dimensional analysis can help out to make sure that you get all your units correct, because otherwise I would be left with kilojoules per joule instead of a unitless equilibrium constant. So just watch out for that. And so plugging this into a calculator, you get about 0.70. And so keep in mind that the equilibrium constant, as I just said, is unitless, and so the answer is just that. B part 2 looks like a conceptual question, so I'll try and fit it in over here. So if both the partial pressure of nitrogen monoxide and the partial pressure of nitrogen dioxide in the vessel are initially one atmosphere, will the partial pressure of N2O3 at equilibrium be equal to 1 atom? Justify your answer. Alright. In something like this, it might help for you to write out your equilibrium expression, your traditional one. So we have K is equal to, this time I'm going to do the partial pressure version. So it's PN2O3 divided by PNO2 times PNO, right? And we're given, after our calculation, that this is 0.70. And so what this automatically means is that the partial pressure of PNO2 times the partial pressure of PNO has to be greater than the partial pressure of N2O3 for this fraction to be less than 1, or 0.7. And so in the denominator we have 1 times 1, and so we have some quantity x over 1 has to be 0.7. We can easily figure out that the partial pressure is going to be 0.7. Or sorry, where the initial one is 1 atom, except the only way that the partial pressure of N2O3 can be 1 atom is if the reaction goes to completion. So we can still use this mathematical proof that because we start off at one atom, we're going to transition a little bit into the middle because it's a reversible reaction. So the partial pressures will be decreased a little bit. However, it cannot reach 1 because the equilibrium value is less than 1, suggesting that there's a greater amount of partial pressure compared to the product. And so the answer, in short, is no. Justifying is because the only way that the partial pressure could be equal to one atom is if the reaction goes to completion, which it does not because this is a reversible reaction. And the other reason why is because the equilibrium constant at 0.7 is less than 1, suggesting that there has to be a higher partial pressure, total partial pressure of reactants compared to products. Okay, moving on to part C. The student hypothesizes that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture. Indicate whether you agree or disagree with the hypothesis. Justify your answer. Okay, so increasing the temperature in this case, well, what do we see? So our delta H is negative 40.4 kilojoules per mole reaction. Okay, so I'm just going to write that in as a part of the reaction. So I'm going to say NO plus NO2 will form N2O3 plus 40.4 kilojoules. Okay, so this is just another way of writing a thermodynamic reaction by including the energy term as part of the actual reaction. And so in this case, it might be a little bit easier to visualize Le Chatelier. And so Le Chatelier says, on a slight tangent, I'm going, that if an equilibrium reaction or if a reversible reaction under equilibrium experiences some sort of a stress, then the reaction system will undergo some process to counteract the stress or to move in the opposite way of the stress. And so essentially, the simpler way of considering it is if you increase your reactant, then the equilibrium process will try to move towards the product to get rid of the excess reactant, to go back to equilibrium. And so, in this case, increasing the temperature, what happens is, so this is what we do. I'm going to mark that in white. So we increase our temperature. What's going to happen is that Le Chatelier says that this temperature is going to decrease because we are going to shift to the left. In response to an increase on the right-hand side, we are going to shift towards the left. So everything on the left is going to increase, everything on the right is going to decrease. And so, based on Le Chatelier's, we can say that we disagree with the student's claim. So we disagree. The reason why being that it will actually decrease N2O3 because Le Chatelier's favors the formation of reactants and the catabolism, you can say, or the usage of the products. Okay. Part D. The skeletal structure of the HNO2 molecule is shown in the box below. Complete the Lewis electron dot diagram of the HNO2 molecule in the box below, including any lone pairs. Okay, so we have H, we have O, we have N, we have O. So think about how exactly we're going to do this. Now we can do this with our valence electrons method where we try and assign, or we can just reason our way out of it. And so what we know is that between H and O there's going to be one pair of electrons. Now oxygen is going to have its two lone pairs and it's going to have one bonded here. Nitrogen is going to have its one lone pair, and nitrogen can form three bonds, and so we're going to have something like this. So you can reason your way out of this by saying that, okay, so hydrogen is going to form one bond with oxygen, nitrogen is going to form the other bond with oxygen, and then we have this oxygen on the side that has to have two bonds, and it can only be bonded to nitrogen. And so the Lewis structure of this, not the dot diagram, but the structure, would look something like this. Or as you may have seen this compound already, it would be something like along the lines of this. Since we normally write an OH group together. And so I drew those, but this one is the correct one. Oh, this is part I, sorry. Alright, so the fairly simple point. And then II says, based on your completed diagram above, identify the hybridization of the nitrogen atom in HNO2 molecule. Okay, this is also a fairly simple one, because for the purposes of AP we only work within SP, SP2, SP3. There's a fairly simple trick that we can use in order to identify the hybridization. And so what we see is that the nitrogen has a single bond and a double bond. I'm going to draw that here. And so what we see is we have a sigma bond, another sigma bond, and a pi bond. And so essentially what you can do is you can count the number of pi bonds and decrease that from the number associated with P in an SP. So we start with SP3. Now we have one pi bond, so we decrease 1 from 3, so it becomes SP2. This is an sp2 hybridized nitrogen. We could also prove this the proper way by going through the electron and the electron orbitals and then figuring out the hybridization based on the number of electrons that we need left for this pi bond within the p orbital, but I find this is a much faster trick to do on an exam like this. Okay, now we get into some slightly more challenging questions, because now we have a titration. So to produce an aqueous solution of HNO2, so we bubble N2O3 into distilled water, the reaction goes to completion, and we only have HNO2. And then we titrate HNO2 with KOH, so potassium hydroxide, at 0.1 molar. We titrate 100 ml of that, and we form the NO2, we form the NO2 ion and water. And we're given this titration curve. There's a fairly distinct buffer, as you can probably see if I redraw this titration curve very quickly in orange. We have sort of a region right about here where there's a very gradual change in pH over a longer quantity. So this is probably going to be a buffer region. Not sure if that'll help out in any of the questions that follow, but just thought I'd include that for your content. Okay, so part I says, determine the initial concentration of the HNO2 solution. Okay, so let's think about how exactly we're going to go about doing that. So let's think about where our equivalence point lies. And so it's where this titration curve has a vertical tangent, so it's about over here, and it's at 20 ml of KOH added. And so essentially what we have to do is we have to take this 20 ml of KOH, we're going to convert it into the number of moles that was added, and then we're going to consider the stoichiometry to figure out the initial concentration of HNO2. And keep in mind that we have 1 ml sample of the solution that we're using, and so we'll find the moles of HNO2 and then we're going to divide by 0.1 liters to get the concentration initially. So just to show what I was talking about, we know that we have 20 ml of KOH, so this is 0.02 liters of KOH, and then we have 0.02 times the concentration, 0.1, to get 0.002 moles. Once we have this, so there's 0.002 moles of KOH. This means that because KOH breaks up into one potassium and one hydroxide ion, it's going to be an equal number of moles of both, and so there's 0.002 moles of hydroxide. If we consider the stoichiometry, for every one hydroxide we have one HNO2, or nitrous acid. So nitrous acid. And so based on that, we know that we have 0.002 moles of HNO2. This is by stoichiometry. Oops. And then we do 0.002 divided by 0.1 to get 0.02 molar, I believe. So yes, 0.02 molar HNO2 solution. Okay, and then that was a terribly. I should be able to fit this on the previous slide. So part 2 says estimate the value of pKa for HNO2. Okay, so when we look at this titration curve, we can see that the pKa is approximately equal to pH at the half equivalence point, right? So we just have to try and approximate where our half equivalence point is. And so if we go back to this diagram that I quickly drew, the half equivalence point occurs, I'll indicate it in blue, somewhere around over here. So in this middle of this line. And so if we look back on the graph, it occurs approximately at where 10 milliliters of KOH was added, and the pH can be approximated to about 3.3 or 3.4. And so the answer that I would give would be 3.4 is our pKa. So it's just knowing that the pKa is approximately equal to pH at the half equivalence point. Okay, now for part F. During the titration after a volume of 15 ml of KOH is added, which species, HNO2 or NO2, is present at a higher concentration in the solution? Okay, so here's where you have to know your terminology of titration. So we've indicated that at 20 ml we have our equivalence point, but at 10 ml we have our half equivalence point. And so 15 is in between, so it's past the half equivalence point, but it's before the equivalence point. So what happens after? So after the half equivalence point, there is a greater amount of conjugate base. Than the conjugate acid. Okay, and so what that means is NO2 minus, its concentration has to be greater than the concentration of HNO2. So it's just important to recognize that the half equivalence point marks the equal concentration of conjugate base and acid, and so after this half equivalence point, you're going to have more conjugate base. So the answer is NO2 minus. All right. Question 3. So question 3a says, write the ground state electron configuration of the Fe2+ ion. Okay. This one isn't too bad. If you recognize your periodic table, I'll scroll back up to it. Keep in mind, so 26 is where iron is. So we know that we're going to have the nearest noble gas is argon, right? So we're going to have argon, then we're going to have 4s2, and then we're going to have 3d6. So I will scroll back down. Okay, so first I'll write Fe. So Fe is argon, 4s2, 3d6. If you don't know how I got this, then I strongly advise you to go revise your electron configuration notes, because especially the thing I'm about to do now is a principle that students often forget when they're talking about ions of transition metals. and that's the fact that even though our 3D subshell has more energy technically than the 4s, our ion, the electrons that are removed for an ion, are actually taken out of the 4s subshell because of its position. So it's at a higher quantum number, so because 4 is greater than 3 obviously, and so we actually take out electrons from this one. And so our Fe2 plus is actually going to be, oops, don't know why I wrote a theta sign, so it's be an E. So Fe2 plus is actually going to be argon 3d6. If you write it at the full, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, without the 4s2 in the middle. Okay, so that was part A. Just a quick trick that they were checking to make sure that you revise that special exception of ions of transition metals. Now part B says the radii of the ions are given in the table above. Using principles of atomic structure, explain why the radius of the Fe2 plus ion is larger than the radius of the Fe3 plus ion. Okay. So, what exactly do we know? Well, what we know is that the nuclear charge, the effective nuclear charge, is the same for both. So I'm going to say that the nuclear charge is the same. However, one of the things that you notice is that Fe2 plus versus Fe3 plus, the fundamental difference is the number of electrons. And so Fe2 plus obviously has an extra electron. And so while you might think that the extra electron means a greater amount of pull to the nucleus, because the nucleus is positive, and thus the greater amount of electrons would mean there would be a greater amount of attraction, and thus it would be more compact, the electron repulsion actually counteracts this to a degree where the ionic radius is larger in the Fe2 plus. So E minus repulsion causes a greater distance or a greater radius within that shell. Causes up radius. Okay, so that was a conceptual question. We don't get many of those, but it is estimated that for some of the upcoming AP exams, especially this year, there's going to be a lot more conceptual questions. Part C says Fe3 plus ions interact more strongly with water molecules in aqueous solution than Fe2 plus ions do. Give one reason for the stronger interaction and justify your answer using Coulomb's law. Okay, so what is Coulomb's law? So Coulomb's law says that the force between any two charges, so Fc, force between two charges, is given by K Q1 Q2 over R squared. And so while you don't need to know this exact formula to actually calculate, all you need to know is that it's proportional to Q1 Q2 over R squared. Right, so the proportional statement is the one that you need to know generally for chemistry. If you're taking physics, for example, though, AP Physics C, electricity, or AP Physics 2, or even AP Physics 1 maybe, I'm not too sure about those, but you would need to know the actual numerical calculations. For this purpose, though, you only need to know the proportionality relationship. And so what we can say is that, well, the Fe3 plus has a higher charge, and so automatically the force is going to be larger, or the radius is smaller. And so there's essentially two reasons. Fe3 plus equals up Q and down R. And so we're decreasing the denominator, we're increasing the numerator. Overall, we're going to get a larger value compared to the Fe2 plus ion. And so that's essentially why we can prove that Fe3 plus has the stronger attraction. A student obtains a solution that contains an unknown concentration of Fe2+. To determine this concentration, they titrate it with the manganese ion. So it's a redox titration, and we convert Fe2+ to Fe3+, as represented in the following reaction. So part D says write the balanced equation for the half reaction of the oxidation from Fe2+ to Fe3+. Okay, well, this is a very straightforward question because you don't have to consider about any of the rules when you're balancing. Because all you had to say was, okay, so we go to Fe3+, and then we have an extra electron. So it's probably one of the fastest points you could have gotten on this exam, or probably on any of the exams, even faster than the drawing question, which was fairly simple as well. Okay, part E says the student titrates a 10 milliliter sample of the Fe2+ solution. Calculate the concentration in the solution if it takes 17.48 milliliters of this potassium manganese at 0.0350 molar to reach the equivalence point of the titration. Okay, so lots of titration questions in this year, which is quite interesting. So essentially the way that we're going to do this, I'll outline it first, is that we're first going to calculate the number of moles of KMnO4 needed, and thus we can figure out the number of moles of MnO4 that's utilized. And then we're going to use our stoichiometry to figure out the number of moles of iron needed to reach that point, and then we're just going to calculate the concentration, similar to what we did in the previous titration question. So that should give you a hint. They're very similar. And so we have 17.48 milliliters, which is 0.01748 liters, times 0.0350 molar, which gets us 0.000612. This is moles of KMnO4. Now, because KMnO4 splits evenly into potassium and manganese, we have 0.000612 moles of manganese, of the manganese ion. And so then we multiply, then we use the stoichiometry, so we have 0.000612 moles of MnO4 times, not 4, 5, sorry. Times 5 moles of Fe per 1 mole of MnO4. And so that should get us 0.003059. And then, now that we have this as the number of moles of Fe, we just have to divide this number, so 0.003059 moles divided by, we're titrating a 10 milliliter sample, and so we have 0.01 liters, and so taking this, we should get 0.3059, so rounds to 0.306 molar Fe2+ solution. So the concentration is 0.306 molar. Okay. F. Explain why the 25 milliliter volumetric flask would be a poor choice for use for delivering the required volume. Okay, so this is where a little bit of lab components come in. So if you don't know how exactly a volumetric flask measures, then you wouldn't have been able to answer this question. But luckily, you're watching this video, so you'll be able to find out for future questions. So, volumetric flasks. What's special about them? They're probably the most accurate way to measure a volume if it's exactly that volume. So volumetric flask, a 25 milliliter volumetric flask, is one of the most accurate ways to measure 25 milliliters. Anything different from 25 milliliters and it becomes wildly inaccurate. And so the reason why the volumetric flask would be a poor choice is because we're only trying to take a 10 milliliter sample. So because the volumetric flask is only accurate for 25 milliliters, so only accurate for 25 ml samples. And so it'd be inaccurate for 10. So that's all that they were looking for. You don't need to actually like draw out a volumetric flask or explain why it's inaccurate. You just have to know that fact. So it was an interesting question that they threw in because not many people bother reviewing the lab component, and if they do, they bother reviewing the like experiments themselves, not necessarily the actual lab materials. So it was a nice question to throw in there to see how well people actually were prepared. Okay. So we have a separate experiment now where we're given some powdered iron with an inner impurity. The student uses a procedure to oxidize the iron into Fe2O3, and we have this data now. So we have 6.724 grams initially, and now we have 7.531 grams of Fe2O3 produced. It says calculate the number of moles of Fe in the Fe2O3 solid produced. Alright, so how exactly are we going to do this? Well, we can find the number of moles of Fe2O3 that were produced, and then we can consider the number of moles of Fe produced within that solution based on how exactly Fe2O3 splits. And by that I mean it splits into three oxygen atoms and 2 iron atoms. And so for every one Fe2O3 you'd have 2 irons. You'd have to multiply by 2. So you'd have to use that stoichiometric ratio. So we have 7.531 grams Fe2O3 multiplied by 1 mole Fe2O3 over, we have to calculate the molar mass again, which is in this case 159.7. Grams. And so we get the total number of moles as 0.04716. Okay, so we have this number of moles. Now we say this is of Fe2O3, and now we say that we have 0.04716 moles of Fe2O3, but then we multiply by, we get 2 moles of iron for every mole of Fe2O3. And so, all in all, we multiply this by 2 and we get 0.09431. Okay. So that's our answer. Part H says calculate the percent by mass of iron in the original sample of powdered iron with the inert impurity. Okay, so we just found out that there's 0.09431 moles of iron. That were produced. And so we can't add iron from anywhere because we're just oxidizing it. And so what we notice is that we can figure out the total amount of grams of iron that we started off with. And then we can just take that number and divide it by 6.724 to get the percent amount of mass. So multiply by the molar mass or the atomic mass of iron, which is 55.85. Not 5, it's 55. Grams per 1 mole, which gets me 5.267. Grams of Fe, and then we go 5.267 divided by 6.724 4 initially. And so working that out, we get 0.7833. So 0.7833 means we have 78.33% Fe. Okay, so that was also a fairly simple question. Part I looks conceptual, but I should be able to fit it in. So it says, if the oxidation of the iron in the original sample was incomplete, so that some of the 7.531 grams of product was FeO instead of Fe2O3, okay, would the calculated mass percent of Fe in the original sample be higher, lower, or the same as the actual mass percent of Fe? Justify your answer. Okay, so if we think about this carefully, if we have any FeO, right, then we're going to have a higher actual mass percent of Fe than a completely oxidized sample, right? And so when the moles are calculated, the calculated number of moles and then the calculated mass percent is going to be lower compared to the actual. So the answer is lower. As you may have known, your justification has to be the actual mass percent So the number of moles calculated and the mass percent has to be lower. Okay, so that is the justification. You can figure out the reason why, because of the amount of iron that would be produced in FeO and Fe2O3, a combined quantity, rather than just Fe2O3. You can do that with some math as well. If you take let's say if you take 6 grams of Fe2O3 and 1.531 grams of FeO, you can also prove that mathematically, or you can just think about it theoretically and just state that fact and you still get a point for it. All right. So that was question number 3. So that marks the end of the long answer questions, and now we're just into what I like to dub the speedrun part of the AP Chem exam, because this is the part that goes by very fast. Alright, so we're given a table with molecular structures and boiling points. In terms of the types and relative strengths of IMFs, explain why CS2 is higher boiling point than COS. They very commonly ask these kind of things. So I'll just create a table really quick. So I'll say CS2 COS. This one only has London dispersion forces. This one also has London dispersion forces, but there's an oxygen bonded to a carbon. So I see dipoles. However, why exactly is the boiling point of CS2 greater than the boiling point of COS? And in this case, by a significant degree. So LDF of CS2 has greater force than LDF and dipole force combined of COS. So this is a question that very commonly comes up, is that you have a compound that has more intermolecular forces but has a lower boiling point. And the reason why is because the number of electrons plays a huge role in the strength of the London dispersion forces. And in this case, as well as in many other cases, we often see that if you consider the number of electrons in CS2, it's quite a lot greater than COS, to the point where the dipoles actually don't matter in comparison to the strength of the London dispersion forces in CS2. That's why there's such a big gap, because the number of electrons is significantly different. Alright, so that was part A, a conceptual question. Part B is a calculation question. It says we have a 10 gram sample of CS2 in an evacuated 5-liter container. The container is sealed and heated to 325 Kelvin. At which temperature is all of the CS2, at which temperature all of the CS2 is vaporized? What is the pressure in the container once all of the CS2 has vaporized? Okay. So CS2 is a liquid, but then it's evaporated, so it's a gas now. Our best friend with gases is the ideal gas law. So PV is equal to nRT. Okay. We're solving for pressure, and so we know that pressure is equal to nRT over V. We're given our V, we're given our T, we know our R, we just have to calculate N. Well, we know that N is equal to mass over molar mass, which is equal to 10 grams times, we just have to calculate the molar mass of CS2. So it's 76.3. Sorry, this is divide, not multiply. Divided by 76 point, sorry, I think it said 76.3, I meant 76.13. So 76.13 grams per mole. And so the total number of moles we get is 0.131. Okay, so now we just have to calculate P. So P is equal to 0.131. Looks like a 10. It's meant to be 0. So it's 0.131. Then we have our R value. So it's 0.08206. 0.08206. The units on this, you don't necessarily have to write it out unless you're doing the dimensional analysis way. Just liters, atmospheres per mole Kelvin. And then we're given our temperature as 325 and our volume as 5. And so working this out on a calculator, we get 0.7 atmospheres. All right. So, just like I said, it's the speedrun part. So we're moving very fast. Okay, 5A. Two particulate representations of the ionization of HF molecules in the solution are shown below. We're given an equation such that hydrofluoric acid and water react to form the fluorine ion and the hydronium ion. The percent ionization is 13%. Okay, explain why the ionization of HF molecules in water in figure 1 is more accurate than the representation in figure 2. The key below identifies the particles in the representation. Okay. Well, what we have to consider is that we have percent ionization. PowerPoint must have glitched a little bit there. Okay, so percent ionization, we're given as 13%. And so what 13% means is that only 13% of the initial acid is going to get converted into the fluorine ion and the hydronium ion. So let's see in figure 1. Well, we have a total of 1, 2, 3, 4, 5, 6, 7. We would have had 8. We would have had 8 HF molecules, and it became 7 HF, and then 1 H3O, 1 F minus. And so if we consider 1 over 8, well, that's approximately equal to, it's 12.5, which is approximately equal to 13%. On the other hand, if we look at fig 2, we would have 1, 2, 3, 4. We started off with 8 HF again, but we got H, 8 H3O, and 8F minus, which would represent a 100% ionization. And so obviously figure 1 just mathematically is going to be more accurate because it's much closer to the 13%. And so this mathematical proof you can use by saying that, okay, figure 1 represents a 13% ionization, but show the actual numbers, that we started off with 8 and one of the acid ions was ionized, so 1 and 8 is approximately 13%, compared to figure 2 with 100%. Okay. B says use the percent ionization data above to calculate the value of Ka for HF. Okay, so this is it's an okay long question. We can say that because for every HF molecule that gets ionized, we form equal concentrations of F and H3O. What we can assume is that the concentration of H3O is going to be equal to the concentration of F minus, right? So this is what we can assume. Now, one of the things that we can figure out is that we have percent ionization as 13%, which is 0.13. So 13%, which is equal to 0.13. Well, this is going to be equal to our concentration of H3O divided by our concentration of HF initially. And our concentration of HF initially was 0.035. And so we can calculate concentration of H3O. I should probably put a plus. So our concentration of H3O is going to now become 0.00455. Okay, so we've done that. We've used our percent ionization in order to figure out the concentration of one of our values. And we know that now we can figure out our concentration of fluorine as well. Okay, now one of the mistakes that people made was they often went directly to the calculation for Ka, but you still have to consider the fact that we're not at equilibrium with the concentration that we're given so far. So we still do have to set up a Rice table. And so I have HF plus H2O. That looks terrible. Forms F minus plus H3O. Okay, and so we have initial, change, and equilibrium. So our initial, in this case, was 0.035. This is non-existent. This is 0 and 0. We just figured out that the concentration was 0.0045. This one was only 0.00455. And I said this must have been plus 0.00455 plus 0.00455. In this case, this one must have been minus 0.00455. And thus this final concentration of HF that we get is 0.034. 0.0304. Okay, now we can calculate our Ka as being the concentration of H3O times the concentration of F over the concentration of HF. Now, because it's all coefficients of 1, there's no squaring or anything, and so we can just plug this in. So it's just 0.00455 times 0.00455, and then divided by 0.0304, and I get 6.81 times 10 to the power of negative 4. When you put it into scientific notation, and generally for equilibrium, you like to keep stuff like that when you get past magnitude negative 3. Alright, so that was our Ka value. Now, part C says, if 50 ml of distilled water is added to 50 ml of our solution of hydrofluoric acid, will the percent ionization increase, decrease, or remain the same? Justify your answer with an explanation or calculation. Okay, there's two ways to go about this. I'll show both ways. I should probably switch to the next slide so I can fit it. So one of the ways, the way that most people did this was by calculating Q. And so what we see is that if instead of adding, so we're doubling the, volume of the solution. And so we're decreasing the initial concentration of each species by 1/2. And so we end up getting Q in this case is equal to 1/2 so 1/2 H3O times 1/2 F over 1/2 HF. Now if you don't know why that is, it's because we're adding 50 ml of water to 50 ml of this acid, and so the acid gets diluted by a factor of 1/2 because the volume doubles. So every single aspect of the reversible reaction now has half the concentration. And so our net thing is going to be 1/2. You can into factor out all the 1/2s and cancel it. It becomes 1/2 times our equilibrium constant. And so because Q is less than Ka, our equilibrium position will shift towards the products. So there is a shift right, and thus there's going to be up ionization. If you just think about this conceptually as well, then if you think about this in terms of Le Chatelier's, now while the water isn't necessarily part of the equilibrium expression, when you dilute the acid, right, you're not going to get as much forward reaction. So Le Chatelier's will say that you're going to try and move forward in order to counter this increase in the H2O liquid. And so because of that, you're going to get more product formed, and ultimately that means more product means more percent ionization. So you could use Q, you could use Le Chatelier's, or you could use the actual calculation as you would normally do with the X's in terms of the equilibrium constant, and then you could actually calculate the new percent ionization. So I'll show you that way as well. So we know, put a squiggly line. So we know that the new concentration of HF is going to be 0.0175 because we divided the original 0.035 by 2. We know our Ka is going to be 6.81 times 10 to the negative 4, and we know that this is equal to H3O times F over HF. And we know that the concentration of H3O and F is the same. So I'm just going to say for both of these, let this be X. So then I get 6.81 times 10 to the negative 4 is equal to X squared over this 0.0175. So X, our value is equal to 0.00345. And then, based on this, now we can calculate our percent ionization. So it's the concentration of H3O over the concentration of HF. And we get 0.2 approximately, which rounds to 20%. And so as you can see, well, 20% is greater than 13%, so there is very clearly an increase. Okay, so just wanted to show you all of those different methods for that question. 6a, the student measures the voltage of the cell above and discovers that it is 0. Identify the missing component of the cell and explain its importance for obtaining a non-zero voltage. So we have a galvanic cell with chromium and silver. Okay, electrochemistry. If you remember the structure of a galvanic cell, I will do a brief drawing with my beakers. So we have one metal, and we have solution, we have another metal, we have the electrolyte solution, we have our voltmeter, where we have stuff moving in some direction. Sorry, I shouldn't specify that right now. We have our voltmeter, and then we have the most important part. I'll indicate it in orange. The component that we're missing, the salt bridge. Okay, so we've identified that we're missing the salt bridge. Now, what exactly does the salt bridge allow us to actually do? Keep writing in orange, because why not? The salt bridge allows for the migration of ions. So, migration or movement of ions to both anode and cathode. To prevent a charge imbalance, essentially, or to ensure that the charge is restored. So to ensure is a charge balance in the cell. So basically what happens is that on one side, so on the anode, where it's going to be positive, we're going to be losing electrons. And then on the other side, we're going to be gaining electrons, so it's going to go negative. And so the salt bridge is going to split its atoms up into its anion and cation to ensure that it counteracts this effect, to make sure that there's no net change in the charge. Otherwise, the cell will just have a zero voltage, because there can't be any sustained migration of electrons. So the salt bridge is very important when you're preparing a cell. So B part I. So now we're given our half reactions. This is the cell voltage, once the missing component is added, is 1.54 volts. The silver ions are reduced. Use this information and the information in the table to calculate the value of E, so our cell potential. For the half reaction, chromium gets oxidized. Oh, sorry, it's the reduction half reaction. Half reactions are always written in the reduction form. So chromium is getting oxidized, but the half reaction is the reduction of chromium. Okay, so this is where you have to keep track of signs very carefully. So we know that depending on which formula you like to use, E cell is equal to, it's the E cathode minus E anode, or E reduction minus E oxidation. The way I like to remember it is that I like to remember the second one usually, because it spells out redox, so you just have to write out redox in order. And so what we get is 1.54 is equal to 0.8 minus x. So my x is automatically going to be 0.74. And now the thing that you have to consider is, if you were to consider sign conventions, you would have to use a slightly different formula where you convert it into the oxidation half reaction and then use a different formula. But the way I like to remember is that half reactions are always written in the reduction form. And so with this formula, E reduction minus E oxidation, all that's telling me is I'm using the half reaction involving the metal that is being reduced first minus the cell value or the potential of the half reaction involving the metal that is being oxidized. But the value you get is still for the reduction half reaction, so I don't have to change any signs or anything for this particular question. So it's 0.704 volts. Okay, For part 2, it says write the balanced net ionic equation for the overall reaction that occurs as the cell operates. Okay, so this should be fairly simple if you look at the electrons. So we have 3 Ag plus Cr moving to 3 Ag plus Cr3 plus. This is a solid, sorry. This is a solid, and the others are aqueous. This is a solid. Okay, so that was a fairly simple, just the net ionic reaction, very quick marks. And this last question is calculate the value of delta G for the overall cell reaction in joules per moles of reaction. Okay, so we use our second application of thermodynamics where delta G is equal to NF E. And so this is Faraday's constant, Faraday's law. And so think about exactly what we need. Well, our N, right? So our overall cell reaction, we have to consider, sorry, it's negative. I almost forgot. It's negative NFE. It's negative. Now the number of moles of reaction, right, is going to be 3 moles of electrons for every 1 mole of reaction. If you think about it, there's 3 moles of electrons that get used up for every 1 mole of reaction. And so we have 3 times Faraday's constant, 96,485. This is coulombs per mole electron, and then times our cell potential, which is 1.54 volts, which is 1.54 joules per coulomb. So our voltage is going to be our energy per unit coulomb, so our joules per coulomb. And then Faraday's constant, coulombs per moles of electron, and then there's 3 moles of electrons per every mole of reaction. And so multiplying these all together, we get negative 4.46 times 10 to the 5th. Joules per moles of reaction. All right. And that marks almost the end. I almost thought that was the end for a second, but I forgot. There are 7 questions, so let's quickly go through this. Question 7, so we're given a PES, a photoelectron spectrum, and we're told to identify the element. Okay. First of all, I see, so our first peak goes up 2 bars, but our first peak in a photoelectron spectrum has to be the sp2. So we're given sp2, or not sp2, sorry, sp1s2. I almost confused hybridization. So sp1s2, 2s2, 2p3. And so we're given that it's 1s2, 2s2, 2p3 just by counting the number of bars, because we have to have 2, and then there's another 2, and then there's one bar higher. So it's 1s2, 2s2, 2p3. We go all the way up to our periodic table and look at what exactly is 2p3. We see that it's this element number 7, so it is a nitrogen. So our element is nitrogen. Okay, so 7a, very quick, just a counting exercise. Part B, now we have rates for radioactive decay. This isn't something that comes up very often, but it is a formula that you guys should know. So the radioactive isotope of an element decays with a half-life of 10 minutes. Calculate the value of the rate constant for the radioactive decay. Include units with your answer. Okay, so essentially the formula is K is equal to 0.693 divided by our half-life, or our decay life, so T1 half, Now t1/2 is 10 minutes, and so we get 0.069. Now the units you have to include, they are a little bit funky because it's inverse minutes, or 0.069 times 1 per minute. So the units are a little bit confusing to recognize over there, but it is what it is. And then part C, if 64 atoms of the radioactive isotope are originally present in a sample, what is the expected amount of time that will pass until only one atom of the isotope remains? Okay, so I'll show you again both ways that you can go about this. The first way is to count the number of half-lives that occur. So we can literally say we go from 64 to 32 to 16 to 8 to 4 to 2 and then to 1. So how many half-lives was that? Well, it was 6 half-lives, right? Count the number of arrows, there's 6. And so we have 6 half-lives times 10 min per half-life. So 60 min, or 1, write my order better, or 1 hour. So it'll take 1 hour for you to go from 64 atoms of this isotope to 1 atom. The other way I'll show you over here is if you remember the rate law. So this is a first order rate expression, radioactive decay. And so what you can do is you can say, well, ln of A at time t minus ln of A at time 0 is equal to negative kt. And so all you have to do is solve for t, and so t is equal to negative ln of, well, our AT is going to be 1. So I'll write this negative a little bit better so you don't get confused. So T is equal to negative ln of 1 minus ln of 64 over our K value, which we found out was 0.069. And so remember, we're dividing by minutes to the power of -1, so our final answer would come up in minutes, and we get our same answer of 60 minutes. Or 1 hour, if you want to be fancy. And so I just want to quickly say that this first expression right over here, ln of A at time t, is equal to ln of A at time 0 minus kt, or this is the algebraically simplified version, is a rate law that I would recommend you guys know, similar to the 0th order and the 1st order rate law. So I strongly advise to remember these. And then just in case if you're wondering, this formula in part B, the 0.693, it is a formula that we're given. It comes from the natural log as well. The natural log of 2 is actually 0.6931 ... So it comes from that, and so you guys can definitely try and check out how exactly that expression is derived. It's an interesting one, if I do say so myself. It involves creating a function for radioactive decay, an exponential function, and then solving for a rate constant based on that. So yeah, that marks the end of the 2018 AP Chemistry Free Response questions. I'd like to just say thank you so much for watching. I really appreciate all of your support on these videos, especially because I know the AP exams are coming up in just a week and a half, I believe they start, because today's May 1st, so maybe they start off very soon. So good luck to everyone on those, and I hope you guys enjoyed this video and learned a lot from it. Please remember to like, comment, and subscribe for any future videos. As I've mentioned previously, I am planning to start right after these AP exam walkthroughs and videos a Calculus 3 and a Linear Algebra series, so be sure to stay tuned for that. Thank you guys so much, and I'll see you guys next time on Patel Academy.